Hello, my name is Hui. I will be talking about a paper on security notions for encryption in a quantum world. This is joint work with Céline Chevalier and Ehsan Ebrahimi. So first, let me give you some motivations for our security model. When we talk about standard security, we usually assume that the adversary are classical and the communication is also classical. But with recent advances in building quantum computers, we also consider post-quantum security, in which the adversary are quantum, but the communication is still classical. So you can go one step further and consider the fully quantum security, in which the adversary are quantum and it's also allowed to have quantum access to the honest parties. So this is motivated by some scenarios like running classically authenticated programs in quantum computers, or they may access some exotic quantum attacks like the frozen smart card attack. So in this work, we study the fully quantum security for the classical encryption. What does it mean to be fully quantum secure? This means that the adversary had quantum access to the encryption oracle, which is modeled by a standard oracle, standard quantum oracle. The adversary has two registers, the input register X and the response register Y, and the ciphertext will be XOR to the response register. And if we consider the chosen ciphertext security, we also need to allow the adversary has superposition access to the decryption oracle. So previously, this was firstly started by Bonet in which they give security notions that allows the adversary to have quantum queries in the learning phases, but only classical challenge query, and they give for both public key and symmetric key encryption for CCI security. And in 2016, Gagliardoni, Hunsen, and Schaffner give another security notion that allows quantum challenge queries, but they restricted to a special minimum oracle. So this oracle have only one register for both the input and the response value, and this is also limited to only symmetric key encryption and CPI security. So the open question is to give a meaningful, achievable quantum security notion in the standard oracle for both public key and symmetric key encryption with CCI security. The difficulties come from the no cloning theorem, in which if you want to copy the quantum queries, this is prevented by the no cloning theorem, and you want to have some information on the adversary queries, you may need to measure it, and by the destructiveness of the measurement, this may be detectable by the adversary. And also in Bonnet paper, they show the impossibility for any left or right indistinguishability notion. So in this paper, we give the first achievable meaningful quantum notion for chosen ciphertext security for both secret and public key encryption. I will give you an overview of our techniques. So first, to bypass the Bonnet impossibility, we switch from a left or right indistinguishability notion to a real or random indistinguishability notion. And to record the quantum challenge query, we adopt the Zandri compressed oracle technique for random oracles to randomize functions. Okay, so let me record Zandri original recording technique. The content of this slide is taken from Zandri talk in Crypto 2019. So the goal of the technique is to simulate on-the-fly random oracles in the quantum setting. This can be described in 4 steps. First, we can purify the random register, the random function. which means that when you sample a uniform random functions, you can put it in uniform superposition and then measure the rest. Then we switch to the Fourier basis by applying quantum Fourier transform to the adversary response raster and the oracle raster. So by doing that, instead of writing data to the adversary raster, we write data to the oracle raster. And here the p, x, and y function is a point function which returns 0 on any input x prime that different from x and returns y on the input x. And the next step is to compress the oracle. We can remove all the points that are not in the query's input, and for any value, for any record in the database that has output 0, we can also remove it. So after Q query, the database has at most Q records. And then the last step, we revert back to the computational basis, which so now the oracle has information about the adversary queries that's stored in some oracle, some database that is hidden from the adversary. And this simulation is perfect for quantum random oracles. Okay, so now we're going to adapt this technique to simulate a randomized function. Here we consider a randomized function f which takes input x and some randomness r. First, we also verify the randomness raster. Instead of sampling a classical uniformly random value r, we can put the r raster in uniform superposition and then later on we can measure it. Secondly, we look at the Fourier domain instead of the computational basis. So we apply quantum Fourier transform QFT to the adversary raster, the adversary response raster y, and the oracle output raster f. And the next step, we compress the database. Intuitively, for any value x that's not in the query input, we can remove it from the full database. And for any record in the database that has output 0, we can also remove it. And the last step, we transform back to the computational basis. However, the above simulation needs 3 applications of the unitary that compute f, which we call UF. Thus, this is not useful for proving one-time security, where you only have one-time access to UF. Or even in some security reductions like Encryption, we refer the reader to the paper for detailed discussion on this problem. Fortunately, in this randomized setting, we can always simulate with only one contour UF because any new query is independent from previous query. So for any new query, we can initiate a new database starting from 0. Now, we're going to use this technique to define security notion for encryption. For the rest of the talk, I focus only on the symmetric key encryption with single challenge query. This can be applied similarly to the public key encryption with multi-challenge queries. So first, let me recall the classical real or random CCA security. This is modeled by the game between the challenger and the adversary. First, the challenger samples a random key for the encryption, and in the first learning phase, the adversary has access to the encryption and the decryption oracle. He outputs a message X and some internal state. Then the challenger samples a random message X1 from the message space, and depending on the bit B, the challenger encrypts XB, and in the second learning phase, the adversary has access to the encryption oracle and some modified decryption oracle, and he has output bit B prime. Here, the decryption oracle in the second learning phase will return bottom if the query is challenge ciphertext, otherwise decrypt normally. Now we make some modification to this security notion. First, instead of returning bottom, we return the original message X if the query is challenged ciphertext. Secondly, instead of sampling a new random message X, we sample a random permutation, and depending on the bit B, we either apply a random permutation to the original message or just apply identity to it. And then we encrypt the result. This doesn't change the security notion, and now we go into this modification to convert it to the quantum setting. So first, we also sample a random key for the encryption. Next, in the first learning phase, the adversary has superposition access to the encryption and the decryption oracle, and he outputs a query, challenge query, which is in superposition of the message X, the Y response register, and some internal state phi X and Y. Next, the transit samples a random permutation, and depending on the bit B, we either apply encryption with either apply random permutation and then encryption, or we just apply the encryption. Here, the ciphertext will be XORed into the Y register, and we use the compressed oracle here to record the query of the adversary, which is stored in the database D. And in the second learning phase, the adversary has superposition access to the encryption oracle and some modified decryption oracle, and he has to output bit B prime. The decryption oracle in the second learning phase is defined as follows. First, we look at the database and we find for any values that is the query input in the database. If found, we return the original message. Otherwise, we decrypt normally. Now, we'll describe some properties and feasibility of our security notion. First, for properties, we saw that classical quantum chance query security notion implies Bonnet-Zandri security notion, which is limited to classical chance queries. We also saw that our security notion is composable, and finally, we saw that having a quantum challenge query is strictly stronger than classical challenge query by showing that even with CCI security with quantum learning queries, but only classical challenge query doesn't imply a CPI security with quantum learning query and quantum challenge query. Interestingly, we saw that one-time path encryption style like stream cipher or some block cipher mode encryption like ZCM, CFP, OFB, or CTR is insecure in our security notion. For feasibility, we saw that encryption mode is QIND QCCA secure, which recovers the classical result. We also saw that in the public key setting, starting from any IND QCCA secure public key encryption scheme, combining with a one-way function gives us QIND QCCA secure public key encryption. And that's all. Thank you for listening.